So what I'll be talking about is joint work with Martin Heirer and a PhD student at Imperial, Martin Peev. Will be graduating soon. All right, and so this should be on the archive hopefully within a month or so. But I'll tell you a little bit about what we're doing. So the beginning of the story is going to be Langevin stochastic quantization. So the spirit here, which is something that's come up in previous talks, is that we're interested in constructing and studying a measure, and we work with some sort of stochastic dynamic to try to make understanding that measure easier. So in yesterday's talks, the stochastic dynamic was one where the role of time was played by scale. So Langevin stochastic quantization is another approach of creating couplings between measures that are hard to understand and measures that are easier to understand, let's say Gaussian measures. Where instead of the time representing a scale, we actually think about the time as representing something more like a time and running a stochastic gradient descent. Okay, so here on the left I have a Gibbs measure on Rn, and if I was interested in trying to simulate or study this measure, then I could look at an SDE on Rn, where the drift term is given by the gradient of that action, and I'm driven by a Wiener process on Rn. And so the idea is that you should be able to hopefully realize mu as, let's say, a long-time average of this random dynamic. So mu, at least formally, will always be an invariant measure of this dynamic. And so then if you work with this process at stationarity, then even though this measure has maybe nothing to do with the Gaussian measure, the fact that I can maybe realize it as the stationary distribution of this random dynamic gives me a coupling with the Gaussian. Okay, and so that again lets us study a harder measure in terms of a coupling of a measure that we understand better. Okay, so so this talk is going to be about the theory of singular SPDE. And so singular SPDE appear quite naturally when you try to employ the same strategy for understanding Euclidean quantum field theories, where instead of a measure on Rn, I have a measure on some space of fields, on some space domain or some space-time domain, and I have some action here. And so if I follow the same prescription, instead of having an SDE, I'll have an SPDE. So instead of being driven by a Wiener process on Rn, I'm driven by an infinite dimensional noise, a space-time white noise. And so what makes these equations very difficult to study on either side is that on the left-hand side, that's a completely formal expression because I don't have a notion of d phi in this setting, so there's no infinite dimensional Lebesgue measure. If S is quadratic, then I can try to make sense of it as an infinite dimensional Gaussian measure. But if S is more linear than quadratic, then it's a difficult problem in general. And then on the right-hand side, you encounter some of those same difficulties. So this infinite dimensional noise is quite rough, and if S is very nonlinear, then its gradient will be very nonlinear. And so this will be a nonlinear PDE in a space of rough distributions, right? So a singular SPDE. Okay. So the idea is that somehow, in terms of applying probability in PDE theory, even though both sides are hard, we have a little bit more help on this side. Okay, so for instance, so this was this approach for studying Euclidean quantum field theories was first introduced or promoted by Parisi Wu in 1981, and they were interested in the case where the measure on the left-hand side was a gauge theory. And so in that case, even when you forget about these issues about ultraviolet divergences and the lack of an infinite dimensional Lebesgue measure, because of gauge invariance, you don't even expect the left-hand side to give you a finite measure. But the stochastic quantization picture, the Langevin one, still allows you to have a probabilistic interpretation when you look at the dynamic. So this picture, you know, that I've put up right now, it's getting, well, there's been a lot of work on it in the case where we're dealing with Q of T's with bosons. And so the departure point, or the kind of place I want to go, is to talk about how we can think about this picture and prove results when we're interested in quantum field theories that have more than bosons, right? Which is what we would want if we want to describe the physical world. If we want things like electrons, which are fermions. And I'll also touch on exploring questions such as large N limits and so-called master fields in this, using the stochastic quantization picture, although I don't have concrete results on large N convergence, but something to say about possible limit points. And so the new ingredient in this story to go beyond bosons is a theory of singular SPDE that also works with non-commutative probability theory. Okay? Good. So, I mean, that was just painting a picture, but any questions so far? Okay. Good. So I want to give a short crash course or introduction to non-commutative probability theory. And so I'll introduce the central characters. So we have a unital star algebra A, which you should think of as an algebra of observables. And to give some intuition in the setting of commutative probability theory, then this algebra is our algebra of random variables. And we think about it as more than just an algebra. We think of it as a space of functions. But in general, you can only realize an algebra as a space of functions when it's a commutative algebra. So in general, we're interested in the case where this A is non-commutative. And so we have a generalization of random variable, and then there's also a generalization of probability measure, which is given by a state, which is a positive linear functional on the algebra that's normalized to 1. And so again, this is really the generalization of the probability measure in the commutative case. And in practice, if you want to actually build a non-commutative probability space, you'll realize this algebra is an algebra of operators on some Hilbert space. And then for the state, it can either be given by something like a trace or perhaps sandwiching with some fixed vector, okay? And so just to recap, so the generalization of random variables will be somehow operators on H, and they don't necessarily have to be bounded operators. So we'll be interested in the case where some of the operators can be unbounded. And so I also want to talk a little bit about random fields. So the idea is that the kind of most general way of thinking about a random field is it's something where you smear it against a smooth test function and you get a random variable. And so in the non-commutative case, what I'm going to have is something where I smear it against a nice function and I have an operator. So the non-commutative way of thinking about random fields is as operator value distributions. Okay. Good. So are the kind of concrete examples that we're going to have in mind are a class, so in order to really introduce the probability, non-commutative or commutative, it always enters through my definition of that space-time white noise when I'm looking at the dynamics earlier. So that's a Gaussian process. In the commutative case, it's just the Gaussian process, which is delta correlated in time and space. If I want to talk about non-commutative stochastic quantization, then I want to introduce non-commutative space-time white noises. So I'm going to start by telling you just a little bit about how you can think about non-commutative Gaussians. And so the starting point, in the kind of operator algebras picture, one way to think about Gaussianity is it's a certain algebra of operators on a Hilbert space that has a Fock space structure. So fix some real Hilbert space, little h. So little h you should think of as being, if you're thinking about building a Gaussian, it's going to be the dual of the Cameron-Martin space. Okay? And so in physics, sometimes they call it the single particle Hilbert space. And then you can build an algebraic Fock space, which is just the direct sum of tensor powers of this Hilbert space. And the first operators that I'll introduce are these creation operators. And so the idea is that for each f in my single particle Hilbert space, I get an operator on this direct sum space, and how I can define it is that just for a given f, it just adds one factor of that f. Okay. And this is our first example of an operator value distribution. So if this Hilbert space is more than just an abstract Hilbert space, but some space of that includes functions, then I can think about this as a space-time pairing, for instance. And so you should think about this creation operator as a creation field, as the operator value distribution. Okay? And we're going to use this operator. Sorry, there's a missing dagger. We're going to use this operator to build a Gaussian field. Okay. Okay. So the next step is going to be to turn this algebraic Fock space into an actual Hilbert space by specifying an inner product. And so the inner product I'm going to define will take the following form. So it looks like the type of inner product you would define on a tensor product of Hilbert spaces. So it's things that have different number of factors are orthogonal. And if you have the same number of factors, then there's a weighted sum over permutations. And for each permutation, the contribution is given by the product of inner products in H. And so this weight is determined by a parameter, which is I'm going to call Q, which you should think of as sitting between -1 and 1 inclusive. And for a given permutation, I raise Q to the inversion number of the permutation. And so I've just drawn a picture of what I mean by inversion number for an example. And so to kind of get some intuition here, if Q equals 1, then this is going to give me a symmetric Fock space. If Q equals -1, it's going to give me an anti-symmetric Fock space. And if Q is not -1 or 1, then it's doing something different. Okay, and I'll say a little bit more about that. So with this definition, I can give you the H that I'm going to use to build my non-commutative probability space. It's the quotient and completion of this algebraic space under this inner product. This creation operator I introduced before descends this setting. And so then the operator value distribution is going to be just the creation operator plus its adjoint, the annihilation operator. Okay, and so again, both the alpha q's are operator value distributions, so this you should also think of as an operator value distribution. Okay, and so I would call this thing this thing would be called the Q Gaussian field. Okay, and so the first question is, why does this thing deserve the name Gaussian? Okay, so again, thinking about this Q Gaussian field, this thing is not an operator. It's something that gives me operators when I feed it in arguments. And so here, what I'm going to do is I'm going to build an algebra, which is the algebra of operators generated by what I get when I smear this guy against the function. And the state is going to be basically taking an operator and sandwiching it against a vector called the vacuum, which is just a distinguished unit vector in the zeroth component of the Fock space. Okay, so and so with these definitions on this algebra, you have something called the Q-Wick rule. Okay, which tells you that if you're looking at the state evaluated on a product of these kind of elementary algebra elements, then you can calculate that as a sum over products of two-point functions. And so here, if Q would equal 1, you wouldn't have to care about what the definition of this crossing number is. And then this thing would just be the normal Wick's rule. In the case where Q equals -1, this is a type of fermionic Wick's rule. So this crossing number, again, I've given a definition, but it's maybe quicker to just understand it by thinking about structure. Okay, so the crossings are actually the crossings of the pairs, right? So good. Okay.
Is it some sort of anyon for Q with between -1 and +1? Is anyonic statistics or something like that?
So you can. There are results in the physics literature where somehow there are kind of systems of bosons and fermions that can generate Q statistics.
But it's, are you in a space of dimension 2?
No, there's no restriction on the dimension of the space here. The other case I want to talk about, other than Q equals plus or minus 1, is Q equals 0, where you don't allow any crossing. And so this is the setting of free probability, where you have a Wick's rule, but you don't allow any crossing partitions. Okay, good. Okay, any other questions so far? Okay. So if the kind of recipe starts with a Hilbert space and a Q. So if you just set H equals R, this is something like defining a single Q Gaussian random variable. For Rn, you can have a notion of multivariate Q Gaussians. So if you set H equal to L2 of Rd, then that's going to give you white noise. And then if you set H to be, little h to be big H minus 1, so again, this is what I mean by it being the dual of the Kaplan-Martin space, right? So that's why it's a -1 there. This is the kind of notational convention here. So this would give you a Q Gaussian free field, which when Q equals 1 matches the objects that are called these things in commutative probability theory. okay? And I'll just mention that, again, in the last two cases, in general, you can't think about these things as operators. Okay, so when you evaluate them at the space-time point, they're really operator value distributions. Good, okay. So, okay, so this is a setting. I've just introduced a whole family of Gaussian non-commutative probability spaces. So what are we going to do with these spaces? Well, for our program, we're interested in solving singular SPDE in these spaces, okay? So I've told you what a Q space-time white noise is, and so I'm interested in solving a PDE that looks like this, where again, this is a PDE where the unknown and the noise is an operator value distribution. Okay, so all the randomness is in the fact that things are operators. Okay, and so it turns out that, so the first thing you can try to do when you're solving a nonlinear equation like this is to write it in a mild formulation and then solve that using a Picard-Lindelof type argument. So you write it as a fixed point problem and you want to show that that fixed point problem is a contraction for small times. And so in order to do that, you need to talk about how you topologize these operator value distributions, and in order to do that, you need to topologize the actual operator algebras themselves. And this actually turns out to be the kind of trickiest part of making this story work of singular SPDs and non-commutative probability theory, at least for the local theory. And I just want to talk already about what this picture looks like in the case of random ODEs, okay? So for Q equals 1, which is the bosonic field, so this is the case where these are really Gaussians in the commutative sense, then the algebra you get is an algebra of commuting but unbounded operators. So if you look at the operator norm of one of the operators in this A1 space, in the language of commutative probability theory, that's an L infinity norm. And so Gaussians, even though they're really nicely behaved, don't belong to L infinity. So if you're looking at a nonlinear equation like this, in the language of operator algebras, so here this is just a random ODE, right? So this is just a Gaussian random variable, this zeta 1. Then it seems like a very hard problem because you're trying to solve a nonlinear equation in the space of unbounded operators, but commutative probability theory tells you that life is not that hard, right? Because you can realize these unbounded operators as spaces of, functions, and then you can work point-wise in the probability space, okay? So here the message is that the fact that you can realize commutative objects as functions allows you to completely ignore the fact that as operators, they're really unbounded. So then I'm going to talk about the Q equals -1 case. So the Q equals -1 case I defined here, it gives you self-adjoint fermions, which are sometimes called Clifford fermions or Majorana fermions. They're different than Dirac fermions, but those can also be worked into the setting, just with some tweaks. So you get an algebra of anti-commuting operators. So things have become more complicated. They're no longer commuting, but at least they have some structure. So since they're anti-commuting, you don't expect to realize them as in terms of an algebra of functions, but that's okay because as operators, they're bounded. So you don't need that point of view. And so, okay, since it's anti-commuting, I don't want to work with a normal kind of power of just one component. But if I look at a nonlinear equation here, I can actually run a Picard-Lindelof type argument using the actual operator norm.
So you mentioned that topologizing is an issue, but I thought that the issues with nonlinearity, that even when you take bounded operator distributions, you have to worry about how you multiply them, right?
That's right.
So you take some kind of a multilinear approach, or how do you do that?
So somehow there's kind of two settings, right? So there's where we're taking values, the algebras of operators, and then there's the space-time we're defined on. And to deal with the kind of singular products, that in spirit is a lot like regularity structures. So somehow the classical theory of regularity structures allows us to understand how to deal with the rough products, but we need to glue onto that understanding how to topologize the target space. Yeah, but there's still kind of other issues that appear, which I'll talk about. Good. Okay, any other questions? Okay, good. So I'll just say that Q Gaussians for Q absolute values strictly less than 1, in some cases they seem worse than the fermions because they're really fully non-commutative, right? So you have this Q-Wix formula, but that tells you something about expectation values. The actual algebra elements themselves don't have any nice relations, but they're all bounded operators again. So we can solve this sort of equation in the operator norm, okay? So that's just a taste of what random ODEs look like. But then I'll move a little bit to the, well actually before I, later I'll move to the SPDE example where we'll have to deal with these singular products that were asked about. But before I do that, I just want to touch on some motivation. So Q equals 0 again is free probability. To motivate this sort of story, I want to reference a result by Grionet and Shilatenko from 2007, where they looked at a certain class of random matrix models. So here, these are random Hermitian matrices, which are weighted by this sort of Gibbs factor, the trace of a strictly convex polynomial. They also looked at a free diffusion. And so the second object may seem a little bit abstract, but I've given you all the abstract tools you need to understand what the objects mean. If you have a notion of Q equals 0 white noise, you have a notion of Q equals 0 Brownian motion. So they also looked at this free diffusion, and they were able to prove that if you look at the kind of long time stationary distribution of this free diffusion, you get a state on a polynomial algebra which matches the large n limit of this state. Okay? So these free diffusions, at least in the strictly convex case, you can connect them to their stationary distributions to large n limits of random matrix models. Okay, and so part of our motivation is, a lot of this analysis went through, Schwinger-Dyson equations. Working with moments, we would like to do a stochastic analysis proof where we just argue at the level of diffusions. Okay, so that's kind of one of the goalposts of developing a theory like this. But I want to move towards singular equations. I'll start with the 542 equation, which is 2 dimensions of space, 1 dimension of time. And so it's a stochastic heat equation perturbed by cubic nonlinearity. And so here, the challenge, so here I'm in the commutative case, Q equals 1. So a problem is that a solution to the linear problem is just a distribution, so you don't have a way of defining the cube. But it turns out that you can still make sense of the cube in a renormalized sense, with this sort of renormalization counter term, and how to actually give this renormalization procedure analytic meaning is to talk about a well-posed remainder problem, where I write the solution to the nonlinear equation as the solution to the linear equation plus a remainder. And if you renormalize using Wick ordering that cube, then the remainder equation for this remainder V is another nonlinear equation where I have additive and multiplicative terms that are given by Hermite polynomials of the linear solution. So these trees correspond to the first, second, and third Hermite polynomials of the linear solution, which is Gaussian. Okay? And so since they're Gaussian, I can define these Hermite polynomials using probabilistic means. I can use a Kolmogorov continuity argument to quantify their irregularity. And once I know their irregularity, in the two-dimensional case, you can show that pathwise in these objects, the remainder equation is well posed. Okay? Again, these trees are renormalized rough products, and so you can use Wiener chaos analysis to construct them. And so I'll just talk a little bit about the picture of Wiener chaos expansions and hypercontractivity. So that's a crucial tool to get good bounds on these trees. So you can think about all of these trees as objects that are living in an L2 space with respect to the Gaussian, and I have non-commutative L2 spaces, just like in the commutative case. And so it turns out that just like in the commutative Gaussian case, the L2 space is isomorphic to Fock space, which I can decompose into homogeneous Wiener chaoses. These are what these HQNs are. And so in order to get really precise regularity estimates on these trees, a crucial tool is equivalence of moments or hypercontractivity, where I can control higher moments of something in a homogeneous Wiener chaos in terms of its L2 moment. Okay? And so there is hypercontractivity for Q equals plus or minus 1, but for Q strictly less than 1, then you have something even better, which I'll talk about why this is so nice and what you can potentially do with this. So these HN should be HQNs, but it turns out you have something called ultra-contractivity, where you can bound the operator norm, the L infinity norm of something in a homogeneous Wiener chaos in terms of its L2 norm. Okay? So the pictures for bosons and fermions is not quite as good as it is for the Q strictly less than 1, but I'll say that for fermions you actually run into some real problems. Okay, let me talk a little bit about a big just overview of a picture of the whole setting. So in Q equals 1, the commutative case, everything is an unbounded operator, right? So if Gaussians are unbounded, Hermite polynomials of Gaussians are unbounded, but all of them are commutative. So you can always realize all of them as spaces of functions and some space of random variables. And this is the setting that regularity structures or other theories of singular SPD work in, where these are all unbounded objects, but you fix a realization of them, and then you solve the equation. And when you fix the realization, you can think about them as bounded. So Q equals minus 1, the primary fields are bounded, but then when you take an object in a homogeneous Wiener chaos, that could potentially involve some renormalization to make its L2 norm fine. I mean, to kind of cancel out the other pieces, to really make it homogeneous. It is potentially unbounded. Okay, so so basically one way to think about it is that for the Gaussian free field, the actual field in the fermionic case can be thought of as an operator value distribution that takes values in bounded operators, but if you form the Wick square, then it's an operator value distribution that takes values in unbounded operators. And what makes life very beautiful is that your earlier trick for dealing with the unboundedness in the bosonic case doesn't work because you're not guaranteed that you can realize it as a function. Okay, so you have the difficulties of bosons without the advantages of bosons. And then for Q strictly less than 1 in absolute value, you're in the fully non-commutative case. So algebraically, it's very bad, but it turns out that both the primary fields and the renormalized fields will all be distributions taking values in bounded operators. So if you can deal with some kind of algebraic problems in terms of regularity structures and renormalization, then the analytic problems aren't going to give you any additional issue. Okay? I'll just say that for the fermionic case, in a prior work that's in CMP, we found a way to deal with the fact that renormalized fermion fields are unbounded by introducing an analog of points. So you can use finite dimensional representations of the bounded operator algebra and find a way to use these to somehow freeze the renormalized unbounded operators. Okay, so I'm not going to be able to kind of talk about that in full to make that explicit, but it gives you a different sort of algebra, which I'll use a different font for, A-1. I want to say that there is an alternative or complementary approach by De Vesci, Fresta, Gordina, and Gubinelli, where what they do is they develop non-commutative LP theory to deal with Dirac fermions. And the issue is, so somehow their theory, I would say for the cases it works in, is more robust. But if you just think about the commutative case, when things are very nonlinear, then solving an SDE in LP is not a good idea. Okay, so it's less suited to very nonlinear problems. In particular, the types of Langevin dynamics we're seeing here. Okay? There's other work I want to mention by Gubinelli and co-authors and Powell Duke, which is studying fermionic QFTs using the Polchinski coupling, which is what we saw yesterday. And I'll say that in the Polchinski approach, you see the renormalization appear, but you're always dealing with objects that you're kind of dealing with trajectories of objects over effective scales. So somehow you never actually run into the problem of defining something like a composite field, like a rough nonlinear object directly. So you actually don't see the issue with this unboundedness of renormalized objects when you work with the Polchinski coupling for the measure. Okay? And I'll also say that our work also generalizes earlier work by Dea and Schott on a rough path theory of Q-Brownian motion. So regularity structures inside of it. So our main contribution is regularity structures in this framework, and it generalizes rough path theory. And so the meta theorem we can prove is that parabolic subcritical singular SPD are locally well posed. Okay, and I'm talking about, I'm not putting all the restrictions here, but basically the things driven by this Gaussian noise that I was talking about, a Q Gaussian space-time white noise. And so we need to run, so in order to do this, we extend the theory of regularity structures. So we need to extend the analytic setting where basically what we're doing is we're replacing R as the target space by some non-commutative algebra. And the general class of topologies of non-commutative algebras we work with are so-called M-convex algebras, which are algebras that are topologized by seminorm, where each seminorm is individually submultiplicative. And so for the various cases, for Q equals 1, this was done in the original theory of regularity structures. There, the seminorms are fixing up realization in the probability space. In the fermionic case, you have to use finite dimensional representations. In the Q strictly less than 1 in absolute value case, you have to use, you can use operator norms. So you don't just have seminorms, you have, it's a Banach algebra, okay? I'll also say that there are issues with non-commutative renormalization. I don't want to get into the details, but I'll just draw, kind of put a picture in that, you know, if you think about one thing that you do in a lot of renormalization group stuff and renormalization in general is that you have to localize objects. So basically you have some kind of structure that you want to extract and you somehow try to factor that structure out. And all I'm saying is that that doesn't, you have to think about that a lot more carefully in the non-commutative case. So even in the so-called the Prada-Debuche argument, you run into problems because you can have something where you have a Gaussian Wick square, but with some sort of like background field or some sort of other operator wedged in between the two factors. And somehow to see that this is a well-defined object takes a little bit of, we actually have to develop just for this problem, a different class of operator norms. I'll say that, you know, what can we do? So for instance, we can now look at the Q543 model, okay? It's locally well posed in C-1/2 space that takes values in the AQ operator algebra I described earlier, okay? I'll say that in this case, the noise is self-adjoint. In the self-adjoint operator algebra case, we can also extend energy estimate methods from the scalar case to a certain degree. So work in progress is proving global in time solutions for these sorts of equations. And what we're also interested in is there's a kind of matrix version of this, where you have a sort of n by n matrix space-time white noise. And so can you show that the matrix SPDE converges to this nonlinear free SPDE, okay, in the Q equals 0 case. Good. Okay, I'll also say that there are also maybe models that are closer to physics. So this is the Higgs-Yukawa 2 model, which is a scalar boson that's coupled with a pair of Dirac fermions. So one thing I want to say is that, you know, one place that you have the Polchinski coupling and you have the Langevin coupling, and they both have advantages and disadvantages, right? So in the Polchinski coupling, one thing you have, the coupling has a really intrinsic notion of scale and independence for good probabilistic properties, but then you also have problems with coercivity and very nonlinear things, okay? In the Langevin dynamic, our coupling may not have such a good relationship with scale, but we can use PDE methods to deal with problems of nonlinearity, right? So some of the large field problem is easier in the SPDE Langevin picture. Good. So for instance, this is an example of a model which we don't know, I would say, maybe I'm wrong, but as far as I know, we don't know how to do using a Polchinski coupling. So what you can do, so in order to make sense, so here I've just written the action. You use the action to define the state. You take the quadratic part of the action to define a Gaussian state. So this is a state that's a product state over bosons and fermions, and then if you perturb it by the interacting part of the action. So this gives you an interacting state. And so you can write down a Langevin dynamic, which is not the naive Langevin dynamic, so that this thing, after a change of variable, keeps the state invariant. And so one thing we're able to do is we're now able to we have a local well-posedness theory for this equation in the types of algebras, these fermionic algebras I referenced earlier. I'll just say that the global theory is more difficult because the Dirac fermions are not self-adjoint. A lot of times with fermionic equations, you work with boundedness a lot, but again, you see we normalize Dirac fermions here. So things become unbounded, but it's something we're thinking about. And so future research questions are, will this open the way to perhaps looking at the stochastic quantization of Yang Mills with ghost fields, right? So in a lot of the work with Langevin dynamics for gauge theories, a tool that's used is the Turk gauge fixing, which is a certain type of dynamic gauge fixing, where you basically introduce a kind of auxiliary motion in the dynamic that doesn't break gauge invariance. In the kind of field theory or perturbative QFP world, people also gauge fix by introducing a new class of particles called Peev-Popov ghosts, which are not really bosons, which somehow deal with the gauge fixing issue. So one interesting question is, can you use this sort of setting to do the Langevin dynamic of gauge fields with ghosts? And then another thing I'll say is that if in the non-commutative case, dealing with, there are more just renormalizable or non-commutative models you can work with. So the kind of most famous commutative just renormalizable model is 544, right? So 5-4 in 4 dimensions. It doesn't exist. We can't construct it. But the issue there is if you look at the RG flow, you can say the problem is that you're trying to construct it for a positive 5-4 coupling. If you constructed it for a negative 5-4 coupling, which you can try to define using some weird tricks, the RG flow does indicate that you should be able to construct this thing. And Kupianen even has a result of doing it in a hierarchical case. But those models are kind of very artificial because the field is unbounded. So you can't just change the sign of the coupling like this. So there's a kind of folklore that in the just renormalizable case, if you're able to change the sign of the coupling, then you can make sure that the model is something you can actually construct. And so these models, these are especially the Q equals 0, the absolute value of Q less than 1, they have good boundedness properties, which indicates that there could be a lot of just renormalizable models that we could construct. And so to the best of my knowledge, a kind of critical Langevin dynamic for a critical quantum field theory has not been constructed yet. So there is work on the gross niveau on 2 dimensions, but that uses the Polchinski flow, not the Langevin dynamic. So I think with that being said, I'll end here. So thanks for listening.